Hi, everybody, and welcome to this week's lecture. What we're going to be looking at today is the movement of water across a cell or plasma membrane via osmosis. What we're going to try to be accomplishing today is we're going to try to look at the differences between intra and extracellular fluid, see exactly where they are, where they reside, and what kind of movement that can happen between the two. We're going to learn why and how, via specifically osmosis, water is going to cross these membranes. And then we're going to learn why and how water is going to be moved and regulated. So let's go ahead and get started. One of the very first things that we need to identify is going to be water in the human body. Now, as many of you know, water is going to be incredibly important. Physiologically, there are a lot of processes that involve water, including the control of neural and muscle activities, blood pressure, the elimination of waste, as well as body temperature. So again, water is going to be incredibly important. And when it comes to water, the human body is going to have two major components where the fluid can be located. Our first one is going to be known as our extracellular fluid. And just like the name suggests, it's just fluid that's going to be located outside of the cell. So looking at this over here, you can see this diagram. We have our extracellular fluid portion and our intracellular fluid portion as well. Extracellular fluid, you can see, is going to be outside of the actual cell itself. So again, extracellular is going to be just anything that's going to be outside of the cell. Some great examples of extracellular fluid are going to be blood plasma, as well as intestinal fluids. Now, when it comes to intracellular fluid, again, just like the name suggests, intra meaning inside, it's going to be fluid that's located inside of the cell. So again, you can see over here, this is going to be our cell, and we can identify that with our cell membranes all around here. And you can also see our nuclei. So again, this is going to be our intracellular fluid. So the main takeaway, extracellular is going to be outside the cell. Intracellular is going to be inside of the cell. So now that we've established that, what we're going to do now is we're going to check out the movement of water across the membrane. So based on yesterday's lecture, remember, water can freely move across the membranes. So again, remember, the cell membrane is made of our phospholipid bilayer. You can see we have one piece here, two piece here, again, giving us our bilayer. And this bilayer is semi-permeable, meaning that we can have water freely move in and out. So again, we have some very specific molecules that have the ability to move in and out whenever they want to. Now, remember, we do have many different types of ways to um, locate or move some of the other components through the cell. And we use them via protein channels, pumps, things like that. Water, again, it can move freely without it, but there are times where we do need to utilize water channels in order to move water very, very quickly. And these are going to be known as aquaporins. Now, all these do is a channel you can see right here, that is specifically used to increase the permeability of water. So basically all this means is this right here will take some time for water to permeate in and out. But again, when we need water very, very quickly, we either need to increase the water content or we need to evacuate it very quickly. We're going to utilize these aquaporins. Again, this is going to allow water to come in very fast and leave very quickly. And an example of this is going to be the kidneys. Kidneys use these aquaporins to maintain water balance by regulating the concentration of urine. So again, water is one of those special molecules that can move in and out through our semi-permeable membrane, through our lipid bilayer. But again, sometimes we need quick movement, so we're going to utilize a water channel known as aquaporin in order to increase or decrease the amount of water in a very short amount of time. So with that being said, now what we're going to do is we're going to look at our osmosis and we're going to look at the movement of this water. So when it comes to osmosis, it's all about water or the diffusion of water. And the way that osmosis is going to work is it's going to be the net movement of water in an area of low solute concentration to an area of high solute concentration. So what this basically means is it's going to go from an area where there's not a lot of solute, meaning the stuff that's being able to dissolve in water, to an area of high. So looking at this over here, you can see our example. We have our water here, and then we have our sodium chloride or our salt. Right in the middle, we have our semi-permeable membrane. So remember, the body really wants to stay at equilibrium. It wants to be equal on all fronts, on all sides. So what it's going to do is it's going to employ osmosis in order to allow that balance to be re-achieved. Right now, we have a very high concentration of water, and over here, we have a very low concentration of water. But subsequently, we have a very high concentration of sodium chloride, and over here, we have a very low concentration of sodium chloride. So what's going to happen is we're going to utilize osmosis in order to equal this out. So what we're essentially trying to do is we're trying to increase the amount of water on this end to equal the increased amount of sodium chloride. Because again, we want everything to be equal. So water is going to move from an area, again, of low solute concentration to an area of high. So all that water is going to rush over to the other side in order to essentially dilute this portion out in order to increase that water. So again, for this slide, osmosis, the main takeaway is that it's going to be the movement of water from an area of low solute concentration to an area of high solute concentration. So let's go ahead and quickly review what our solutions are and exactly what solute and solvents are. So remember, when it comes to our solute, it's the substance that's being dissolved. And when it comes to our solvent, it's a liquid that's doing that dissolving. When we add those together, we end up with our solution, which is a mixture of both of them. So again, the concentration of our solute in a solution is equal to the amount of solute dissolved in a given volume of a solution. So again, how much of this is dissolved into this, making this. Now, there's going to be a couple ways of measuring the concentration. One way to measure it is going to be molarity. And all molarity basically means is how much stuff we actually have in 1 liter of solution. So in this case, our typical units are going to be millimoles per liter. So again, all molarity is the number of moles in a solute in 1 liter of solution. So how much of this do we have in this? Now, there's going to be a couple other ways to kind of see how much we have, and those are going to be osmolarity and osmolality. So the major difference between these two is they're still measuring the concentration of solute in a solution, just like molarity is, but the major difference between these is we're either looking at it as a liter or as kilograms. Okay, so again, osmolarity and osmolality are still measuring the solute concentration in a solution right here, but it's going to do it in a couple different ways. It's either going to measure it in our liters or our kilograms. Okay, so to summarize this entire slide, our solution is made of a solute and our solvent. A solute is a substance being dissolved. Solvent is a liquid that's doing the dissolving. When you add those together, you end up with our solution. Our concentration is dependent on how much of this we have in this, giving us this. We have 3 ways to measure this: molarity, and our units are typically millimoles per liter. We have osmolarity and osmolality, and again, they're both measuring solute concentration in a solution, but this one is doing it via liters and this one is doing it via kilograms. All right, so this brings us to our very first test for knowledge. So what I want you to do is to go ahead and take a couple minutes to see if you can answer questions 1, 2, 3, and 4. We'll go ahead and go over 2 and 3 as a class. So I'll go ahead and give everybody a couple seconds now to pause and give that a try. All right, welcome back. So number 2 and number 3, I feel, are very important to know. So in number 2, it's essentially asking exactly all of these vocabulary terms. So in our extracellular fluid, again, that's going to be fluid outside of the cell. Extracellular, exit outside of the cell. Intracellular, remember intra, inside the fluid, found in the cells. Osmosis, remember, is the movement of water from an area of low solute so the stuff that's being dissolved by liquid, to an area of high solute. Solute, remember, substance being dissolved. Solvent is doing the dissolving, so it's the liquid, again, that's dissolving. And then our solution is just a mixture of both of our solute and solvents. And then number 3, it says in osmosis, water will move from an area of low solute to an area of high solute concentration. Okay, again, remember, it's moving from an area of low solute, that stuff that's being dissolved, to an area of high solute. All right, so let's go ahead now and take a look at osmotic homeostasis. And all that basically means, it's a really big way of just saying how the body is going to regulate and keep everything equal. So when it comes to homeostatic or homeostasis, remember, it's all about the body wanting to maintain a specific range. So in this case, looking at this diagram here, you can see our normal levels, our homeostasis, the net movement of water is going to be equal, meaning that we have an equal amount of water coming in as we have leaving. So again, this is exactly where we want to be. This is where the body works the best. Again, we want to make sure that everything is equal on our intra and extra. So I'll put E for extra and I for intra, just for this example case. Everything is exactly equaled out, so everything is going to be perfect. Now, whenever we're dealing with abnormal situations, there's going to be an imbalance. So in this case, we have our sodium concentration. And because we have that imbalance in sodium concentration, remember, we have our solute, stuff that needs to be dissolved by water. We have a much higher concentration at one end, meaning it's going to cause that water to move, again, from the area of low, so where there's less sodium, to an area of high, where there's going to be more sodium. So looking at this over here, you can see we have our low sodium here, represented by these green dots. And then we have our water. So you can see that we have a much higher concentration of water here, and we have a much lower concentration of sodium here. So in this case, what's going to happen is we're going to take all of these waters and we're going to move them to the area of high, area of high, in order to dilute this down so we can have more of an equalized sodium content. So again, you can see we have our net movement moving down in order to increase the water concentration here, causing an equilibrium. So let's go ahead and take a look or continue about our osmosis, and we're going to look at the 3 situations we have when it comes to the movement of water across our cell membranes. So one of the very first ones we need to know is going to be our isotonic. When it comes to isotonic, that basically means that everything is equaled out and everything needs to be exactly where it needs to be. Again, you can see isotonic, iso meaning equal. There is an equal amount of intracellular fluid and our extracellular fluid. And you can see this right over here. This is going to be our example. We're going to be utilizing a neuron, and you can see that our extracellular fluid is going to be about 280 millimoles per liter. Our intracellular, you can see, is 280 millimoles per liter, meaning we have the perfect balance. We have the equal amount of water coming in as we do coming out. Again, exactly where we want to be. Looking at this over here, you can see our net movement of water across this membrane is going to be equal. We have the same amount on the outside as we do on the inside, meaning again, we have water coming out and water coming in equally. So remember, isotonic is going to be an equal amount. Now, our next example is going to be a hypertonic solution. So in a hypertonic solution, what that essentially means is that there's going to be less somewhere. So we're going to quickly read and look at this case study, and we're going to apply this to our diagram down below. So it says a 42-year-old male hike, 42-year-old female hiked from Colorado River to the Grand Canyon. The temperature was 112 degrees Fahrenheit up Bright Angel Trail, and at 1.5 miles rest house, she placed an emergency call and complained of exhaustion and nausea. She reported drinking 6 liters of water within the last 3 miles. Test reveals that the solute levels were at 250 extracellular, where our normal value should have been at 280. So what happened here is because she drank so much water, she caused an imbalance. There's tons and tons of water now on one side versus the other. So in this case, she greatly increased the amount of water in her extracellular fluid, again, causing a reduction in our solute, meaning that we have much more on the inside. And again, the body wants to maintain everything equally. So what's going to happen is a ton of water is going to rush in. Because again, we have lots of solute in here, and we have a lot of solvent out here. So we want to equalize everything out. So again, water is rushing in. So this situation is known as hyponatremia. Hypo meaning low, natremia, sodium. So in this case, she had low sodium because we had tons of water rush in. One way I kind of remember this is hypo, just like a hypodermic needle is used to inject things inside. In this case, hypotonic, water from the outside rushed inside. So again, you can see that in that movement here from our extracellular fluid to our intracellular fluid. Again, we had a much lower sodium content out here. We had a much higher sodium content inside. And the reason why is because this woman drank a ton of water, increasing the amount of water on the outside. And again, the body wants to maintain equilibrium. So again, a ton of water is going to rush in to try to bring down the sodium content on the inside. Okay, so our last one is going to be known as our hypertonic solution. So in this case, we're going to go ahead and take a look again at our case study. Older individuals who rely on others to obtain water or have an impaired thirst mechanism can become dehydrated and experience hypernatremia. A 75-year-old patient has plasma, extracellular fluid solute levels at 330 millimoles per liter. Normal solute should be at 280. So in this case, this person has a high plasma extracellular fluid sodium outside, causing them to go into a hypernatremia. Hyper meaning high, natremia, sodium. So they have high sodium. And again, this is producing a hypertonic solution. So looking at this over here, you can see we have our extracellular fluid. The concentration amount is at 330. So that's going to be a massive, massive amount. So that means we have tons and tons of sodium on the outside. You can see our intracellular fluid is about 280. So again, we have a much lower amount on the inside. So again, the body wants to maintain equilibrium. So what's going to happen is water is going to rush out because it wants to knock this sodium back down. It wants to decrease the amount. By doing this, we're losing water on the inside of the cell, causing the cell to shrink, giving us dehydration. So again, seeing this over here, you can see the net movement of the inside. Again, remember, we have high amounts of water here, and we have a much lower amount of water here. Because again, this 75-year-old patient is going to be very dehydrated. So again, there's less water here, meaning we have a higher concentration of sodium. So again, water is going to rush out of the cell in order to maintain homeostasis or be equal. So again, hypernatremia, we have water leaving, and this can cause cells to shrink, again, giving us dehydration. So on this slide, what I'd like you to do is either star or circle, do whatever you need to do to kind of remember this, because this is going to be a really, really good way to kind of take all of the different types of situations and putting them all into one spot. So looking at our first one, we see we have an isotonic solution, homeostasis. This is exactly where we want to be. We have about 280 on the outside, 280 on the inside. Again, everything is exactly where it needs to be. We have equal concentrations on the outside and inside, meaning we have equal amount of water coming in and out. So this is perfect because we have the exact or equal amounts of fluids and concentrations. When it comes to our hypotonic solution, remember hypo is going to be low solute in our extracellular fluid. So in this case, we have a much lower amount here. The concentration has dropped. Although our intracellular fluid is normal, what's going to happen is we want to equal everything out. So because we have less here, we have much more water, and we have less water here, in comparison, water is going to rush in, wanting to equal out. So in this case, it can cause hypernatremia. I'm sorry, hyponatremia. And in this case, it can cause cells to swell due to overhydration. Because then we have tons and tons of water on the outside, and we have less water in the inside. And again, because our sodium levels aren't exactly equal, water is going to want to rush into the cell in order to equal it out. And then the exact opposite is happening with our hypertonic solution. Hyper, high solute in the ECF. So what's happening here is we have tons of sodium here, meaning we have less water on the outside. So what's going to happen is we want water to move out again because our inside intracellular fluid is going to have higher amounts of water in comparison to our extracellular. So what's happening is, again, we're trying to maintain homeostasis. So we want this water to come out. So the water is leaving the cell. Because of that, it's causing the cell to shrink, causing dehydration. And again, this is going to be known as our hypernatremia because we have a situation where we have high solute or high solution sodium versus hyponatremia where you're dealing with a low sodium. So this right here is going to be another one you would want to star circle just to make a note of. And essentially what's happening here is this is going to be an example of how it can affect humans. Now, I know we were looking at a neuron, which is going to have to do with the brain, but we're going to look at exactly what's happening in each one of these different types of situations and how it can affect the brain. So remember, normal homeostasis, everything is going to be equal. So 280, 280, exactly where we want to be. Everything is equaled out. We have an isotonic solution. So this is perfect. We have equal amounts of movement of water in and out of our extracellular and intracellular. Hypotonic, the brain is going to begin to swell. The reason why is because we have a higher amount of sodium right here, and we have a lower amount of sodium here. So what's going to happen is water wants to equal everything out. So you can see right here on this dotted line, water is moving over in order to compensate to bring this back in the middle. Again, trying to hit equilibrium. So because of that, you can see that the brain is swelling. In comparison to our normal, when everything's exactly where it needs to be, you see it has all this space, all this kind of buffer zone. You can see because water is moving in, it's increasing the size, causing the brain to swell. And this is going to increase the pressure on the inside. So this is not a good situation. So this is not where the body wants to be. We also have a hypertonic solution where the brain is going to shrink. Now, again, this is the opposite or inverse of our hypertonic solution. What's happening here is we have our intracellular fluid, and again, we have much more sodium on the outside. So what's happening here is, again, since we have a higher concentration of water here, water is going to want to move in, or I'm sorry, outside of the cell in order to bring this back into the middle, because again, it wants to make sure it's equaled out. And because of that, and because we're losing so much water on the inside of the brain, you can see that the brain now is shrinking. So again, it's decreasing in size because it's losing a lot of water on the intracellular fluid to go to the extracellular. So again, these can be some symptoms of our osmotic imbalances: nausea, vomiting, headache, confusion, loss of energy, drowsiness, fatigue, muscle weakness, spasms, cramps, restlessness, irritability, seizures, coma, and even death in some severe cases. So again, the effects of osmosis is going to be very important when it comes to the human body. All right, and that is going to conclude our lecture for this week. So what I'm going to do is I'm going to give everybody a couple seconds to pause this, look at these questions. There are going to be a lot of questions, and then I'll go ahead and show you the answers to them in the subsequent slides. Okay, and then those are the answers for the first one. One of the ones that I would definitely put emphasis on is going to be this over here, matching the terms with the correct definitions. ISO, remember, equal. Hyper, greater. And then hypo is going to be less. So it's in all correlation to the extracellular fluids and to our intracellular fluids. And we're remembering water. Which one is higher and where is it trying to go? Okay, this is going to be number 2. Okay, and then those are the answers to this one. And then finally, these are our last set of questions. And then there you go. These are the answers to those as well. All right, and with that being said, that is going to conclude the lecture for this week. So again, as always, if you do have any questions, comments, concerns when it comes to anything we've gone over, please feel free to ask, and I'd be more than happy to help you out. I look forward to seeing everybody in the next lecture.